Find the nth term of the sequence. So you'll be used to doing this lower down school. So usually you just go, right, that's got a common difference of 3. So that tells me that the nth term is going to be of the form 3n. And then if I write out the sequence 3n, and substituting in when n is 1 for the first term, that would give me 3. When n is 2 for the second term, that would give me 6. And 9, 12, 15, and so on. And so I can work out the difference between the sequence 3n and this sequence here. And the difference between these two sequences is 1, because if I subtract that, the 4 take away the 3, I get 1. So I can tell from that the nth term of that sequence is going to be 3n plus 1. And I can check that by substituting in, say, 5 to make sure that it gives me 16, which it does. Another way of doing that would be, which you probably won't have thought about before, is by something called equating coefficients. And this is something that's quite useful, particularly with harder questions. So I know that the answer to this is going to be in the form some number a, n, plus some number b. So all I'm going to do is fill in the information that I have for each value until we can work it out. So when we've got 1, we know that we've got, in effect, we've got a times by 1 plus b equals 4. So if we just tidy that up a little bit, because a times by 1 isn't the kind of thing that we want to be writing, we've got that a plus b is 4. Now for the next term, as we move on 1, we've got, again, a times by n, which is now 2, which will give us 2a plus b. So we've got that 2a plus b equals 7. What I've just very quickly made is two simultaneous equations which we can solve by subtracting number 2 take away number 1. That will give us a equals 3. So going back to my general formula here, I've got 3n plus b. So now I just need to work out the value of b. Well, if I substitute back into here, into this initial equation, we've got that 3 plus b equals 4. Therefore, b must be 1. So the answer, again, exactly the same as before, gives us 3n plus 1. So that's two different methods of working out the nth term of a linear sequence. Okay, so find the nth term of the sequence. And this sequence doesn't go up by a fixed amount every time. So it's not a linear sequence. So instead of having a common first difference, this has got what you call a common second difference. So as before, if we do this a little bit, 2 on 12 goes 10, and then we've got 16, we've got 22, and we've got 28. Now, the second difference is the difference between these two next bits. These next bits, 10 and 16, 6, 16, 22, 6, and 22 and 28 is 6. Okay, now for a quadratic, we know that it's going to be written out as an squared plus bn plus c, just like any regular quadratic you're probably used to seeing is ax squared plus bx plus c, just with the n because we're dealing with sequences here. Now, if we start with our term numbers, 1, 2, 3, 4, 5, referring to term 1, term 2, and so on, if we substitute in the numbers into the general form, we'd have for the first term 1 squared times by a, which would give us a plus b lots of 1 plus b plus c, and that would be term number 1. Term number 2, in effect, would be 2 squared times by a, which would give us 4a plus 2b plus c. And term number 3 will be 3 squared, which is 9, so we're going to have 9a plus 3b plus c, and I'll do one more. So 4 will be 4 squared 16a plus 4b plus c. Now, we can show why that second difference is important and how we know that that's a quadratic. So if we find the difference between these things, we'll find that that first one has a difference of 3a plus b. Difference between this one is 5a plus b, and the difference between these is 7a plus b. So when we look at the second difference of the general form, we find that they have a second difference of 2a. So what that is effectively telling us is that if 2a equals 6, then the value of a must be 3. So this term, if that is 6, then the value of a will always be half of the second difference. So we could go in and use that now to work out the rest of the nth term. So we know 2a is 6, so a is hence 3. So I know that it's going to be written 3n squared plus bn plus c. So now I'm just going to write out the sequence that would be generated by 3n squared. So that's 3 lots of 1 squared, which would be 3. 3 lots of 2 squared will be 12. 3 lots of 3 squared will be 27. 3 lots of 4 squared will be 48. And 3 lots of 5 squared will be 75. So now what I'm going to do is I'm going to take that away from the original sequence. So my original sequence, take away my 3n squared. Okay, so 2 take away 3 gives me minus 1. 12 take away 12 gives me nothing. 28 take away 7 gives me 27, sorry, gives me 1. 50 take away 48 gives me 2. 78 take away 75 gives me 3. So that's the difference between the sequence 3n squared and my original sequence. So now all I need to do is find the nth term of the bit that's remaining. Well, now I can do what I did with the linear sequence a minute ago, which is that it's going up in ones each time, and that tells me that it's going to be 1n or n. But if I wrote out the sequence n, then I would just have the numbers 1, 2, 3, 4, 5. So what I've actually got to do to manipulate that to get from 1 down to minus 1, from 2 down to 0, is I've got to take away 2 each time. So when I put this all together, I get that this sequence is 3n squared plus n minus 2. Let's just give it a quick check to make sure that it actually works with 5. So I've got 5 squared, 25, 3 lots of that gives me 75, plus on another 5 gives me 80, take away 2 is 78, and it works. Now, there is another way of doing that, and that's using what you call equating the coefficients. So we best have a look at doing it that way as well. So if I know that it's going to be written like that, because that's my quadratic sequence, then straight away I can just take that in and substitute in 1 for all of the values of n. So for the first one, I know a plus b plus c must have a value of 2. Because if I put 1 into there, I get a plus b plus c, and I know that that outputs 2. For the second one, again, if we do what we did a minute ago, we've got 2n squared, we've got n squared, so 2 squared, 4a plus 2b plus c, and I know that is going to output 12. And if I put 3 in again, as we did a minute ago, I get 9a plus 3b plus c, and that gives me 28. So it builds a nice little system of simultaneous equations that you can solve in order to find the value of a, b, and c. So to do this, well, there's lots of different ways of approaching this, but if I do, let's say, number 2 take away number 1, that will give me 3a plus b equals 10. And if I do, let's say, number 3 take away number 2, that would give me 5a plus b equals 16. So from there, that tells me that if I subtract these from each other, I'm going to get 2a equals 6, and hence a equals 3. And that is what we expected from a minute ago. And then I can just substitute back into the others to find the value of b. So if I know that a is 3, I've got 3 lots of 3, plus b is 10. So b must be 1, and that's what we saw a second ago. And c, hence I'll go back into one of the other ones. The first one looks like a good option here. Got 3 plus 1, which is 4, plus c to get to 2. That must be minus 2. Both equally valid methods of working out the nth term of a quadratic sequence. So we'll do both methods with just one more example. So first of all, we'll go with the second difference approach. We'll find the difference of these. So that gives us 11, that's 19, that is 27, and that's 35. And the common difference, second common difference of all of these is 8. Now, for the reasons that I proved to you a minute ago, I know there that effectively 2a is going to be 8. So therefore, I know that my sequence is going to begin with 4n squared. So if I write out the sequence 4n squared from term 1, 2, 3, 4, 5, I'm going to be getting 4, and I've got 2 squared, which is 4 times by 4, which is 16. Got 3 squared times by 4, which is 36. 4 squared times by 4 is 64, and 5 squared times by 4, which is 100. So now what I'm going to do is take my original sequence and subtract the one that I've now got. So that will give me 5, 4, 3, 2, and 1. So now I need to find the nth term of this sequence that's resulting. So it's going down by minus 1 every time, which is enough to tell me that it's going to be minus n. So if I wrote out the sequence minus n, that would give me minus 1, minus 2, minus 3, minus 4, minus 5, and so on. So I can work out how I get from the minus n sequence up to the one I'm now dealing with. Well, every time I'm adding on 6. So that must be 4n squared minus n adds 6. We'll also just do it the other way around as well. So we'll do it by equating the coefficients. So if I just write out the general form, and then I know straight away a plus b plus c must equal 9. I know that 4a plus 2b plus c equals 20, and I know that 9a plus 3b plus c equals 39. And I can just solve this little system of simultaneous equations in order to work out what a, b, and c are. So do what we did before. 2 take away number 1 to give us 3a plus b is 11. 3 take away 2 to give us 5a plus b is 19. Taking one of these away from each other gives us 2a equals 8. So a is 4, which is just what we said a minute ago. So I know it's going to be 4n squared. Substituting that back into the top one here gives us 3 lots of 8. It will be 12, plus b is 11, so b must be minus 1. And then substituting back into our other one, we've got 4, add minus 1, which is 3, plus c, which is 9, so that must be 6.